And we're live.
Very good. Welcome everyone to an interlude session of the chemistry series. We're going to go back and pick up the thermodynamics talk that we've been doing for the past couple of weeks. Next week, hopefully. I just have an interlude. Got a request from someone if we could talk about chirality for a session, and so that's what I'm doing now. And it also helps that I didn't get a chance to prepare the thermodynamic slides for this week. And that also brings me to another topic that whatever you guys want us to talk about here, you can make a request and we will accommodate. Uh, Slides today are not numbered. Sorry. So we're just going to go by the number of slides in the series. The first one being the title slide. So
I'm following your slides. So whatever you slide you're talking about, when you point to it, it will be on the screen.
very good. So we're now on second slide, rotation of plane polarized light. Where does chirality come from? Chirality comes from the observance that some compounds have the ability to rotate the direction of a plane polarized light. So we have these devices called polarimeters, and they shine polarized light. And you put a sample of the compound in this polarimeter, and you measure the number of degrees by which the polarity of the light is rotated. This was a phenomenon that was known to people before people really understood what molecules are and how all of this happens and all that. This is a kind of a theme in chemistry, in that you can do most of organic and inorganic chemistry without knowing any physics and without even knowing what the molecules actually look like. And this is how we used to do chemistry prior to the 20th century, when we didn't know that atoms have nuclei and their electrons and this and that. We still did chemistry. We still made compounds and things like that, because you really don't need to know what goes on in there, as long as you can identify the compounds by their physical properties. So one of the physical properties that chemists used to check for was this rotation of plane polarized light. And they call some compounds dextrorotatory. Those are compounds that rotate the light in a clockwise fashion, and levorotatory, the ones that turn the light in a counterclockwise fashion. Now, as it happens, our bodies, all biology, deals with chiral compounds, and almost all biological compounds are levorotatory. They're L. So when you go uh, to your health food place to buy tryptophan to help you sleep, it's L-tryptophan. And you see a lot of L before the amino acids or before the names of amino acids. That kind of means that it's the levorotatory isomer. So where does all of this come from? This ability to rotate the light. Where does that come from? And now that we know physics, so on the next slide, slide 3, I'm going to introduce the concept of chirality. Chirality comes from that word. I have no idea how it's pronounced in Greek, probably chair, which means hand. And so chirality means handedness. Why hand and handedness? Uh, in the cartoon, we see on the top we have our left hand and our right hand. The left hand and the right hand are mirror images of each other, as you can see in the picture. But if I put them on top of each other, they are not superimposable. So the left hand and the right hand are non superimposable mirror images of each other. Now, this is completely different than a bottle. We see that a bottle and its mirror image are completely superimposable on each other. So things that are kind of like our hands, they have handedness, and so they are chiral. So chiral molecules are molecules that the mirror image of the compound, the two mirror images of the compound are non-superimposable. Where does this property come from? And by the way, we're totally open for people come up and ask questions, and this being a conversation. I don't get a chance to read the chat very often while I'm talking, but please come up and talk. So, yes, John.
So I was just going to say, I think this is right. But for instance, if I were to take a mirror image of that bottle laying on its side, it wouldn't be superimposable because it would be
Absolutely.
reversed. And so so chirality really is about, ultimately, I think about objects that have no axis of symmetry. Is that right?
Awesome. So that is like in 4 or 5 slides down. Yes. So basically giving the game away. If within the molecule you have an internal plane of symmetry, meaning that if the molecule inside of it has a mirror, then that molecule is not chiral. So a hand inside of it is no there's no mirror inside of a hand, whereas a bottle there's a mirror that cuts it in half vertically. Now, if you put the bottle on the side, then the vertical mirror there isn't going to be any vertical mirrors. So yeah. So how do we get this mirror images and stuff? If we go to slide 4, this comes from uh, the structure of a carbon atom inside of a molecule. We saw that for carbon, we have 4 substituents around it. Methane is kind of simply shown this way, but we have seen in the past that this is not the structure of methane. Instead, on slide 5, we've seen that methane has a tetrahedral structure where the carbon atom is at the center of a pyramid, a triangular pyramid, and the apices of the pyramid are the substituents of the carbon. In the case of methane, all 4 hydrogens. Now you would see that this methane now has an internal mirror image, an internal mirror plane, an internal plane of symmetry. The plane of symmetry will include 2 of the hydrogen atoms and the carbon. And then that plane of symmetry will cut exactly in between the 2 hydrogen atoms. So because methane has that plane of symmetry inside of it, it's an achiral molecule. Now, if we go to slide 6, again, we show this mirror plane. This one is it's a butane. On the top, we have a butane. And we see that that's an achiral molecule, meaning that it is not a chiral molecule because this molecule is superimposable on its mirror image. So if I take the left molecule and kind of rotate it within the plane of the paper, if I rotate it by 180 degrees, then I would get the molecule that's on the right-hand side, and they would be superimposable. But in the bottom one, which is 2-hydroxybutane, now these are mirror images of each other, but they're not superimposable. Because if I again rotate the molecule so that the methyl would be on top of the methyl, CH3 is on top of the CH3, CH2CH3 is on top of CH2CH3, then we'll see that the OH will be on top of the H and the H on top of the OH. So these are non-superimposable mirror images of each other. And so the bottom molecule is a chiral molecule, the carbon center that has the 4 different things attached to it is a chiral center. So something I just mentioned, to get a chiral center, to get a carbon that gives handedness, you have to have 4 different things attached to that carbon. Because as soon as 2 of those things are the same as each other, you can have a mirror plane going in between those 2 things. Kind of like in the top molecule, when it's just a butane, I can have a mirror plane that includes the CH3, CH2CH3, and the carbon in the middle, and the 2 H's are on different sides of that mirror plane. But I cannot draw the same mirror plane in the bottom molecule, or any kind of mirror plane in the bottom molecule. And on slide 7, we kind of see the superimposability. I'm kind of really hammering it home because this superimposability is absolutely critical to get non-superimposable mirror images on each other, and to be able to look at the molecule and see if it will be superimposable on its mirror image takes a lot of practice and building models, etc. So you can then be able to think about it pretty quickly. But as I said, the shorthand, the quickest way to that, to finding it, is if you have 2 identical substituents on the carbon, then you're dealing with an achiral molecule.
Yeah, I was just going to say, I mean, that is real. I'd never really thought about that, but that's such a beautiful, clear thing. You get a chiral center if and only if all 4 things are different. That's great.
Yes. Yeah, absolutely. So we saw that we get 2 different isomers, right? These are called I have a slide with terminology in it, so you guys will have all of these definitions in front of you. But these are stereoisomers of each other, meaning what? Meaning that the same atoms are connected to each other, but in a different orientation. So in on slide 7, when we look at the top, the red compound and the black compound, we have the exact same connectivities, right? We have a center carbon, a methyl, a chloride, a hydrogen, and a hydroxide. These are all connected in the same way, but in a different orientation. That is, between the black and the red, the H and the OH have switched places. You see them, so these 2 compounds, the non-superimposable mirror images, are called enantiomers. And these enantiomers are identified differently. Biologists call them plus and minus, or D or L, and that's because they're dealing with, again, the plane polarized light. So plus molecules go clockwise. They are D, dextrorotatory, and minus molecules are L, lever rotatory. But chemists need to be a lot more exact than that, because we have to be able to look at the molecule and tell which enantiomer it is, not to be able to synthesize it, then go look in the polarimeter and see what it does. So what we have is on slide 8. What we do is that we put the substituent with the lowest electronegativity in the back. Usually that substituent is a hydrogen. So we put that in the back, meaning that it is going into the plane of the paper. And so you're looking now at 3 substituents that are looking you in the face. And you go around based in the order of decreasing electronegativity. So bromine is the most electronegative, followed by oxygen, followed by carbon. So on the left-hand molecule, to go from bromine to oxygen to carbon, I go clockwise. That means I go right, or retro. So that's the R compound. On the left one, to go from bromine to oxygen to carbon, I go counterclockwise, or to the left, or sinister, and that's the S compound. So chemists talk about R and S configurations when they're talking about enantiomers. Biologists talk about DL, or plus minus configurations, when they're talking about enantiomers. Questions on that? So go ahead.
So I put Snidely Whiplash up there for the sinister thing. Yeah, I don't know if you mentioned that sinister comes from Latin for left or something,
Yes.
right?
Yeah, it is.
Um,
Yeah.
and
And retro for right.
and
Yeah.
and the way a physicist would think about that is that the one molecule, you take your right hand, stick your thumb into the page, and look at which way your fingers are curling. And the L one, you would do the same with your left hand, or just take your right hand and stick the thumb out of the page and see which way your fingers are curling to
No,
get those
no.
directions.
So
No?
R and S don't necessarily correspond to D and L. That is, not all R's are D's and all S's are
Okay.
L's.
So that maybe gets to my next question, because I was going to say it sounded like you were saying that by doing this, you actually determine which way the plane of
No,
polarization.
no.
Okay.
You can't. The plane polarization is an experimental outcome.
Okay.
You
Okay.
can you can't a priori determine that.
Good.
But
Because I was going to ask how that worked.
yeah, so some R compounds are L, some R compounds are D. So you don't. It all has to deal with the experimental outcome. There's no correlation between them. So slide 9, I'm showing again the internal plane, the mirror. We've talked about that significantly, so I'm not going to talk anymore. It just the square here shows where the mirror is, or should be, in the compound. So let's go to slide 10. This is an interesting concept, in that you can have chiral centers in an achiral molecule. So in this compound, each of the 2 carbon atoms that are pointed to are chiral centers, meaning that each one of those carbon atoms have 4 different substituents connected to them. And at that carbon center, we don't have an internal plane of symmetry. However, the molecule itself has a plane of symmetry. So I can cut the molecule in half and put one chiral center on top, one chiral center at the bottom, and I see that I have a mirror plane. This compound, even though it has chiral centers, it is not going to be a chiral compound, meaning that this compound will not rotate the plane polarized light. Compounds like this, when there's when a mirror plane separates the two chiral centers, are called meso compounds. Meso, I think, means in between or something like that. And so these are meso compounds. So just because you have a chiral center doesn't mean you have a chiral compound, and just because your compound is not chiral doesn't mean you don't have a chiral center. You have to study the or analyze those separately.
So in this case, what if I switch the locations of the H and the OH on the top one? Does that do
Yes.
anything?
Then you will have a chiral compound.
Okay.
And as because you then lose the internal plane of symmetry, then it no longer is a meso compound, and so we get to it. That compound is going to then be a diastereomer of this compound. We're going to get to that in 2 slides. So on slide 11, I'm going to talk about some of the terminology we've been using. I kind of debated whether I should start out with this or not. In any event, it's here. So what we've talked about, chiral center is the same as a stereo center, which is a carbon that has 4 different substituents. Now, I say here carbon because we're dealing with organic chemistry. This doesn't have to be a carbon, right? So in organometallic compounds, a metal center can be chiral. In ammonia compounds, you can have 3 different substituents on the nitrogen, and with the free electron pair, that makes 4 separate substituents on nitrogen. So then that can become chiral. Oxygen that carries a plus charge that has 3 substituents, again acts like a nitrogen, that can be chiral. But in organic and biological chemistry, when we talk about chiral centers, by and large we talk about carbons. So a chiral molecule is a molecule that doesn't have an internal plane of symmetry. That is, it's a molecule that can rotate the plane of polarized light, the direction of the plane polarized light. Stereoisomer are molecules that have the same formula and the same connectivities, but the orientation space differs. So we saw the stereoisomers that were 2 enantiomers, that is, the 2 non-superimposable mirror images, are stereoisomers of each other. Enantiomers are mirror images of each other, non-superimposable mirror images, because if they're superimposable, they're basically the same compound. They're not isomers. And diastereomers are compounds, and we'll discuss this in a little more detail. Diastereomers are compounds that have more than 1 chiral center, but they don't form mirror images of each other. The stereoisomers are not mirror images of each other. Slide 12, a couple of more things. Racemates or racemic mixtures is a mixture that contains both enantiomers, both R and S. And so a racemic mixture does not rotate the plane of polarized light because it has both R and S in it. For some of you, I mean, if you are diabetic and you inject insulin, you probably know about racemic insulin. That means that the insulin molecule that you have in there has both of the stereoisomers, both of the enantiomers in it.
Is the implication that the concentrations are the same?
The implication is that in a racemic drug, half of the molecules you're ingesting aren't going to work. Only half of them.
Right, but to be racemic, I mean, according to the definition, it would have to be equal concentrations, I think.
So that goes to what we call EE, the enantiomeric selection. So you don't always get a 50-50 mixture because some reactions, depending on, we're going to talk about the Ray-Psi phases. Those phases aren't always exactly the same. And so thermodynamically, the reaction will favor one enantiomer or diastereomer than the other one.
And then the result, presumably, is that the plane of polarization does rotate.
Does rotate, yeah, because you can end up with reactions that like E is 65% or 70%, meaning that it's 70% one, 30% the other, things like that. It's you do end up with reactions that are not 50-50. And then the act of separating out the two enantiomers to have, a bottle of R and a bottle of S, it's called resolution. So you resolve the racemate, or it's a resolved racemate, things like that. So these are some terminology stuff for this. So slide 13 shows the relationship between enantiomers and diastereomers. So in the top left molecule, we see that we have two chiral centers. They're identified both as R. And if I go across with a pink arrow, I have a mirror image that is not superimposable. And so those two are enantiomers of each other. At the bottom, so RR and SS. At the bottom, I have the SR isomer on one side and the SR isomer on the other. Those are also superimposable, non-superimposable mirror images of each other. So those are also enantiomers. But if I look at the stereoisomers that are connected to each other by the blue arrows, they're not mirror images of each other. They have absolutely nothing to do as far as mirror image is concerned. They're neither mirror images nor superimposables. However, they have the exact same connectivities. So when you have two or more stereoisomers, then you're going to form diastereomers. And as we see on the next slide, slide 14, enantiomers have identical physical properties. So given physical means that chemists use to separate compounds, you cannot separate out enantiomers from each other. And these physical means are kind of like chromatography, crystallization, distillations, things that we use to purify compounds. We cannot separate out enantiomers by these means. Diastereomers, however, are different molecules. They have different physical properties. They have different melting points, different boiling points, different polarities, different interactions with chromatography columns, etc. So they can be easily separated out by physical means. So the way we separate out enantiomers is that we react that enantiomer with a single enantiomer of another molecule. So we have, let's say I have a mixture of S and R compound. I reacted with only an R other compound. So now I end up with a compound that has two different chiral centers. So now I have SR and RR. These are now two diastereomers of each other. I can separate them out using chromatography or distillation, and then cleave the other compound that I added to. So this is how we resolve enantiomers. You have to make diastereomers out of them, separate out the diastereomers, then convert them back to the enantiomer they were.
Quick question, Sam, if that's all right.
Yeah.
The enantiomers, can biology separate them out? Can enzymes and things? Because I know in biology that
Absolutely.
chirality can.
Yes.
So that's why you're being specific about your chemical means can't. But okay, thanks.
Yeah, because biology is an optically active environment. So meaning that all the molecules in our body are chiral molecules, and so they only interact with one enantiomer and not the other. So the body does that, and as we said, you so for those of you who are depressed and you take Lexapro, Lexapro first came out as citalopram. And citalopram is the racemic mixture of the SNR enantiomers. Sorry, that wasn't Lexapro. That was Celexa. Celexa was the mixture of S and R enantiomers. And then they were able to separate out the two enantiomers and figure out it was the S enantiomer that is biologically active. The R enantiomer is not. So then they came up with S-citalopram, which is Lexapro. And so the dose of Celexa and Lexapro are different by a factor of 2. That is, if you take 10 milligrams of Celexa is the same as taking 5 milligrams of Lexapro, because the 5 milligrams of the R compound is just goes away, doesn't do anything.
Thanks, buddy. And I think you've just set a load of people's virtual assistants off by keep saying Celeste, which sounds alarmingly like Alexa.
Yeah. Sorry. All right, so the last topic here is prochirality. Prochirality means that we start out with an achiral molecule, but the molecule can undergo reaction on two different sides, right? I have that aldehyde shown there, that any new addition that can happen, it can happen either from the top or from the bottom. And most of the time, these two faces are identical to each other, so you get a basically 50-50 distribution of reactions at the top and the bottom. So the reaction at the top or reaction at the bottom lead to compounds that are non-superimposable mirror images of each other. So following the addition reaction, you end up with an optically active compound, a chiral compound. Because the reaction from an achiral gives a chiral, the achiral compound is called prochiral. And the face that gives rise to an S enantiomer is the psi phase, and the phase that gives rise to the R enantiomer is the ray phase. And this is where you might get, depending on what that R group is, because of steric hindrance, the bulkiness of that R group and how it is bulky, and is the rotation around that CR bond free, or is it slightly hindered? That is going to give you kind of differences between the re and psi phases, which either kinetically or thermodynamically will differentiate between the two phases, so you don't end up with a 50-50 racemate. That's all. Questions?
Hey,
So
great, Sam. I wonder if I can ask a couple questions. First of all, thank you so much. I kind of always feel like stereochemistry, isomers kind of it's difficult to understand, and I'm glad you can explain things really well. And like John, I especially like your conclusion. Like say, if you have a carbon with a four different uh, the substitution, then you would have the chiral center. Then the way you did, the way you described it is put the least electronegative atom away from you. Then the remaining three just kind of go the sequence by the electrical negativity. And if it's the highest to the lowest, if they are crosswise, there will be R. If they're countercrosswise, there will be S. Now, reminds me, I think the R and the S, they react with light different. Is that correct?
Yeah, that's you may not have been here at the beginning. I started the talk by saying that we kind of became aware that such a thing is going on by realizing that compounds, especially biological compounds, rotate the plane polarized light either clockwise or counterclockwise.
Okay.
And so we started
Got
giving them DNL names, like for dextrorotatory and levorotatory. And then once we figured out structures of compounds and atoms and stuff, then we came up with chiral centers and RNS afterwards.
Yes, great. And but actually, I still have sometimes I still have a trouble to get that mirror imaging, and I think the sometimes I look at my hand, the left and the right. I think so. You probably kind of said that probably is the better. You rotate it in the center, then 180 degrees. See if that not interpose each other. That will be the chiral, and it's not kind of left to right. Slide from the left to the right, and um, is that right?
So let's go to slide 6. I think that's the one that explains it the best. So in the top molecule, I want to see if I can superimpose those two molecules, the ones on the top.
Yeah.
I'm on slide 6. So I put the methyl over the methyl, and so I have to rotate the left compound 180 degrees around an axis that goes in and out of the plane. So if I rotate it 180 degrees, then I can put the methyl on top of the methyl, the CH3 on top of the CH3, and the ethyl, the CH2CH3 on top of the CH2CH3. When I do that, I'll see that one of the hydrogens is on top of one of the hydrogens, and the other hydrogen is on top of the other hydrogen. So these are superimposable. They are mirror images because I can see the mirror plane and they're mirror images, and they were superimposable. Now I'm going to do the same thing for the bottom one. If I rotate the molecule in the plane of paper for 180 degrees, and I put the methyl, the CH3, on the CH3, and the ethyl, the CH2, CH3, on the ethyl, then now we see that OH is now at the bottom and H is on the top. So the OH and H won't superimpose. So those are non-superimposable mirror images of
Right.
each other.
And yeah, in that case, in this case, it's at the bottom one is also for different kind of uh the
Yes,
substitution.
yes, yes,
Yeah,
exactly.
yeah.
Yeah.
And so sometimes I kind of get hung up is say the like a household item. Say that if you have a left glove and the right glove, they has to be chiral. But if you have a gun and uh, definitely you kind of lefty and the righty, they will use them differently. Is that considered a chiral or not chiral?
Yeah, yeah, yeah. In fact, the word chiral comes from the Greek word for hand, and they're called chirals because they behave like our hands in the same that they're non-superimposable mirror images of each other.
So the gun would consider be chiral item.
The what?
Gun, just kind of handgun or
They have a gun
No,
in
no,
the
he's, no,
hand.
he's asking if a gun would be considered chiral or handed. And I would say it depends what level of detail you look at it. If you don't consider which side the safety catch is, for example,
Yeah.
then it would be not it would be symmetric. But if you consider the details such as which side the safety catch is, I think it is asymmetric and therefore chiral. That would be my guess.
Yeah, unfortunately, I don't know much about guns. All I can tell you is that if you can basically have a mirror
so what about
bisecting the
the
gun in half, meaning
yeah,
that you can put a mirror in there so that the right side and the left side are exactly the same, then it's achiral. If they're
right?
different, like it has a button on one sorry, it has a button on one side but not on the other, then it would be asymmetrical, and so it's going to be chiral.
Okay. So what about the water bottle?
Yeah, so go to slide 3, and that showed that water bottle was an example of an achiral object because within the water bottle I can have, in this case, a vertical mirror plane that makes the right side of the water bottle and the left side of the a single one, not in between the two water bottles, but within a water bottle. A mirror plane bisects the water bottle in half so that the right side and the left side are going to be identical. So then that becomes an achiral object.
What you have the bottle screw and on the top.
You can keep adding things to it. My answer is going to be exactly the same. If you have a mirror inside of the object that bisects the object into two identical right side and left side, then it's achiral.
So even the bottle cap, the screw is only kind of one direction. So you use the right hand open the bottle cap, would it be feel different from the left hand open the bottle cap?
If you have a screw, then you don't have a mirror image.
Thanks.
If
Yeah.
they're both right hand screws, then they're not they're not mirror images of each other.
Okay.
Right?
Okay.
The mirror image of a right hand screw is a left hand screw. So if they both bottles have right hand screws, the screws are not mirror images.
Okay. Thanks again, and it's a very good kind of the PowerPoint. It's helps a lot. Thanks, Sam.
Sure. I'm glad it was useful.
Yeah, that was good. Testing my understanding a little bit. In a prochiral molecule, the Re and Si sides would, I think, depend on what it is you're planning to add as a constituent, or as a whatever um, appendage, whatever constituent, whatever
Substituent.
substituent. Is that right?
Um, yes and no. Well, I mean, the thing is that if R prime that I'm adding is identical to R, then I'm going to end up with an achiral
Right.
because,
No,
right?
but ultimately, the point. I guess my point is, it depends on the electronegativity of the substituent that you intend to add.
Ah, but see, the thing is that then the ray and the psi faces are named differently,
Well,
right?
that's what I meant.
Yeah,
So in other
ray.
words, the point is that the ray and psi sides aren't properties of the molecule; they're properties of the molecule and the substituent that you intend to add.
Yes,
Yeah,
absolutely,
yeah.
absolutely. So ray and psi are determined based on the product. If the product is R, then this face is going to be the ray face. If the product is S, then this face is going to be the psi S. So without knowing what the product is, you don't know if you have a ray or psi face. And so basically, I think this is what you were saying is that I, if I change R prime, then my ray and psi faces also change depending on their
Right,
respective electronegativities.
right.
Yes,
No, I was just testing
that's
my
correct.
understanding, and I just gave myself an A. I think I got it.
Yes, you did. Absolutely.
But I want one more thing, though. You said at the very beginning that most organic molecules are L rotate, I guess, the plane of polarization the
Biological.
same. But why
Biological.
is that? Why? I mean, why would that be?
It's, evolution. It's by chance. It's the first dominant biologically active molecules were L. So basically, subsequent to that, everything becomes L.
I guess I
It,
don't. I guess that's the process. I'm not. It's not clear to me why. Just because this kind of molecule is an L, it's going to favor other molecules that are L. Uh, that's not a priori obvious to me.
no, it is not. Hopefully, in future sessions when we talk about the interactions of enzymes with molecules, we can see why that is.
So I just gave myself another A.
Yeah, I mean, Wisdom is right too. It's not at all obvious. You kind of have to go through it and then say, oh yeah, now it makes sense. So there is this concept in chemistry. Well, my one of my former lab mates, who's a faculty at Notre Dame, he spent his career on this. In that, some compounds, when you do a reaction, you end up with 50% RNS, but somehow the R product that you get catalyzes the formation of more R, whereas the S doesn't catalyze the formation of more S. And so the theory is that somewhere along the way, at some point in our biological evolution, we had this situation in which one enantiomer catalyzed the formation of its own enantiomer. This at first was like really, really out there until in the late 80s, early 90s. Tom Cech proved that RNA can catalyze the formation of RNA, and so RNA enzymes, and he won the Nobel Prize for that. So the question was, well, why is it that then just the lRNA causes the formation of more L, and that became clear that some enantiomers do this, and so I mean it is not a proven concept. It is just that this thing happens. So it may have been that early on in the biological processes, we had this fork in the road, which kind of led to one L instead of the other one.
Can I squeeze in one more, Sam?
Yeah.
All of this is very new to me. Although the idea is easy to explain, but you mentioned at the beginning that being chiral or achiral would affect the molecule's interaction with polarized light. And I don't see why. Maybe you don't. Maybe this is for another episode. But maybe you can tell us how is it that this happens.
Um, I will ask John to answer that question because that's a physics question, not a chemistry question. I guess I should know this, but the thing is, I don't care.
I think
As long as it
he
gives me
has
the
double
answer.
A's. I think he has double A's. He should be able to answer.
Yeah, and I apologize, Shamash. I just got distracted and I didn't listen at all to what you said. Can you repeat the question? Sorry.
Yes, of course I can. We mentioned at the beginning that being chiral or achiral or R or S would change the way polarized light interacts with the molecule. And I just don't see the connection between it being arranged in a certain way and polarized light doing something to it. I don't know why that happens.
Oh, yeah. Well, I don't know that I can give you any. I mean, I think probably even if I understood it at that level, I don't know that I could convey that understanding to you. I know what it's based on, but ultimately, it really is just the fact that if a molecule has any effect on light, then if it is chiral, it shouldn't be surprising that that effect would be to rotate. One effect would be to rotate a polarization plane one way or the other. Now, it's important, of course, the difference between plane polarized light and so-called circularly polarized or unpolarized light. These are all kind of different things. But in plane polarized light, the electric field vector oscillates back and forth in a specific direction, right? And so if that's interacting with a bunch of molecules that are kind of randomly oriented, but have a chiral property to them, um, then, well, that's not the way to look at it, I guess. Yeah, I think I'm not explaining it very well, but it's certainly not surprising to me that that would happen, and it would be based really just on the fact that these molecules aren't the same. Rotating them in one direction, then rotating them in the other, so they have different effects on light in one direction than the other. That was kind of a bullshit explanation, but maybe the best I can do.
Yeah, maybe we can do a bits of physics on that one day, like a
Oh, don't.
cross between Sam and John.
Yeah, let me look into it too because we have this kind of spectroscopy technique called circular dichroism that we use in biological compounds, and it's used for both DNA and proteins in that it measures the extent of helicity in the compound, and it does it again using plane polarized light and the rotation of it. So if you have a right-handed helix or a left-handed helix, and what percentage of helical compounds you have, it basically uses the same concept. And I can ask my wife to explain that to me because she used that for her thesis all the time. So hopefully next week I can give an answer.
It feels like we ought to be able to give a very simple answer that you can get by just looking at your two hands. So, question before I try and come up with that: what is it the case that for differently handed molecules you can distinguish them with Circularly polarized, plane polarized, both? What's the situation? And both plane and circularly polarized light distinguish
Just
charged
plain.
molecules? Just
Just
So
plain.
plain.
yeah, so circularly polarized light can be thought of as a combination of two linearly polarized light beams that are 90 degrees out of phase. I
Yeah.
think maybe you might be able to figure that out, right? And so, my first guess would be, and it's kind of a guess, is that if the chiral, mixture affects both of those separate linear polarizations the same, you ought to end up at the end with still just circularly polarized light.
Can you not also describe it the other way around though? Couldn't you describe plane polarized light as a equal mix of left and right-handed circular polarizations?
Yes, you can. And so then the question would be, so let's see, so then when you are right, so the circularly, just think about circularly polarized light first. Both of the planes of polarization would be rotated the same amount. You'd end up with circularly polarized light, but the two components would now have different phases. And so if you do that same kind of thing with thinking of the linear polarization as being a combination of two circularly polarized light, one gets advanced in phase, one gets retarded in phase, and the result is a plane that has rotated.
I'm still trying to get to a nice explanation where you just look at your two hands in front of you and you reason either via the circular or the plane route, because I think we just decided you can argue about it from either way, right? Because they are superpositions of each other. I'm sure that you can just look at your hand and give a test case by which the different polarization would lead to a different result, but I haven't quite worked out what that is yet. I'll think about it.
Hey, Sam, I have a follow-up question. I think if I kind of working in the lab, and when I do the identification, other than the light polarized lights, what are those isomer they would respond to the other spectroscopy like the uh, NMR or mass would be very similar results, and the how their physical property difference, like the boiling point, other I can use to separate them.
Yeah, on enantiomers you can't. So spectroscopy, they show up identical, boiling point, melting point, all physical properties are exactly the same. So enantiomers, you cannot physically separate them. Diastereomers you can, because if they're non-mirror images of each other, then they're different compounds and they have different physical properties, different melting point, boiling point. So you can crystallize them differently, distill them, or column chromatography, any of that stuff that normally is used to separate compounds, you can use to separate out diastereomers. So usually, if you want to separate out enantiomers, what we do is that we react it with another enantiomer. So we form two different diastereomers because of that. And then we separate out the diastereomers, then we cleave off the enantiomer that we added. So that's that's really the most common way of separating out enantiomers. Otherwise, physically you can't.
So I've stared at my hands while thinking about this. John, what do you think of this? It's hard to imagine on Clubhouse, but you look at your two hands in front of you. They are different. They are mirror images of one another, non-superimposable mirror images, like these molecules Sam's saying that light can distinguish. Now, if you just cast a beam of light, just look as you look at your hand, imagine the light that you're looking at your hand, imagine coming out of your eyes as a helix, spiraling, let's say clockwise. And imagine that helix, which is a metaphor for the circular polarization of the light, um, interacting with your left hand. It's going to hit, if this thing coming into your eyes is leaving your eyes and going clockwise, it's going to hit your thumb first, then your index finger, then your next finger, then your next finger, then your little finger. Whereas if it hit the other hand, polarized the same way, it would hit the index finger, and then it'd have to go around over half a rotation before it hit your little finger, and things would be in a completely different order. So I think you can see that with circularly polarized light, it just physically reaches the different parts of the molecule at different parts of the phase, depending on whether it's left or right hand.
Yeah, I think that's a kind of an analogy that only goes so far. It's very similar to thinking about polarized sunglasses. A common thing is to say, well, if it's like a wave on a string, and you're running that string through a slat back chair, and you oscillate the string up and down, then the wave will go through because the slats are vertical. And if you oscillate it back and forth, it won't, because the slats are vertical,
Yeah, that only
etc.
works
But
when
the
you've got one filter, right? When you start doing stacking filters.
Yeah, right. And it's worse than that, because it's kind of just the opposite of what really happens with a polarizer, in some sense. That idea of letting it through just turns out to be kind of a weak analogy with what's really going on electromagnetically. So it's not a bad way to understand how left-handedness or right-handedness can treat things differently, but I don't think it's a very good analogy for what's really going on when
Yeah, I think
when
I
the plane
agree.
of a light wave is rotated. Yeah.
So you could zoom out a little bit and not make up and that weak analogies, and just simply say this: when you look at your hands, which you're entirely doing with light, you're using light to distinguish the handedness of your two hands. So therefore, light can distinguish the handedness. And then the
And I think
details of that you can
if
go
you
into.
think about if you think about a plain polarized light going through a mixture of molecules that have no chirality, then it should be pretty obvious that whatever the electrodynamics are, it's not going to rotate the thing one way or the other. You've got these molecules that don't have any chirality to them, all oriented randomly. Um, there's no conceivable reason for that to rotate the plane of polarization one way or the other, just as a kind of a fundamental argument from symmetry. So it's more of an argument for the rotation, saying that in general you should expect the plane to rotate, but the only way it could possibly rotate is if the molecules have some chirality.
I can't really contribute to this conversation because it's all physics.
Well, it's really more math than any. I'm just
Yeah.
making symmetry arguments, right? I'm not giving you any physics.
Yeah, it's one of those things that it's like, yeah, it's nice to know, but a lot of things are nice to know. So I don't know. I never was curious enough with respect to that. All right. If there aren't any more questions, we shall bid you farewell. So, Shamash, what's going on this Wednesday?
Hopefully, we will take some historical examples. I was working on another mathematical room that has to do with Bayes, but then I decided against it. But the more I do this, the more I discover how bad that like background philosophy, the entire thing just falls down very quickly. So
Thank you,
maybe
Shamash.
I will. So maybe I won't do it on Wednesday. We will take some historic examples, like 4 or 5, and then we will ask people, what do you think of this from this point of view or that point of view? So it'll be like a nice review for all the philosophical points we've seen before we move on to discussing other things. Yeah, that's the plan. Thanks.
Sounds good. John, what are we doing Friday?
I don't know for sure. I've been talking about, and I may end up doing this, starting kind of just a series that will be very long and probably not sequential. as kind of a basic physics course. And and if I do that, I think each one, the nice thing about it is I think I would take it in really small chunks. So I'm thinking about if I were to start, if you were to take an introductory physics course that I designed completely, the first thing I would do would be to talk about static equilibrium. No acceleration, no velocity, not just stuff that is held in place by, so that it doesn't move and it doesn't rotate. And so I'm thinking of kind of introducing that idea by thinking about a bar held in place by some ropes attached to it, and how does it decide how to end up in state, the idea of stable equilibrium, the idea of equilibrium in general, et cetera. Just a few things like that. And then we'll talk about forces and torques for a while, and then maybe at some later time talk about what happens when forces and torques aren't balanced. At the beginning, we'll just talk about forces and torques in balance so that we have statics. So that's kind of my very sketchy idea. The problem is I have very little time between now and Friday. I have friends visiting, and so I don't even know what I'm going to be able to get done. If I do something like that on Friday, it'll be just a really short introductory thing.
Yeah, you
John,
can
And
do. Sorry.
if you're
sorry.
struggling, John, I could help with that. If you give me an
I
if you just give me a very rough outline of the scope of the first one,
I may do that. We'll
I can
see. Yeah,
do
thank you,
you one on
Benjamin.
statics, either hand drawn, or I'll do slides to keep it consistent with yours.
Yeah, I found a way to stream both ways, so you can have the slides on a scene, and then I have the tablet with me on the other scene. If you recall, when we did this one time, John, when we were drawing acceleration vectors and so on. So whatever slides you prepare, I can always augment them with the hand drawn thing. I think we're okay.
Good, great. Really appreciate it, Shamash. It's it's a lot of effort on behalf of Sam and me, and really appreciate, and yourself, of course, you do it.
Yeah, absolutely. Ben, do you have any rooms scheduled for this week or just
No,
random
I
pop
don't at the
ups?
moment. Yeah, random pop-ups. Just keep an eye out in the Smart View house every, for random pop-ups with well moderated with clear guidelines.
Yeah,
But
yeah.
no, I'm not going through like a series of topics at the moment. I'll come back to it at some point, most likely. But yeah, not right now.
Let me also mention Hero, Andy. I have mentioned before, and I would still always love to do that. Maybe hand over a bite one week for a presentation on LiDAR kinds of things, or whatever you think along those lines. What there must be some fun stuff you could talk about. So I won't push you on that, but just so you know that I'm still eager to have something like that happen if you wanted.
So that'd be fun for me, anyways.
Well, if you wanna work on something like that, just let me know when you're ready to do something, and we'll do it.
All right, I'll I have a presentation somewhere that I called "What is lidar." Um, I gotta find that because I got some kind of nice graphics in there already. I'll look around for it.
I'm surprised they just did start the lidar for the Egypts or the pyramids in Egypt and found all that stuff underground, and they just barely found that out in 2025. But lidar, from my understanding, has been around for a long time. I'm curious why they just tried it for the first time in 2025. Does anybody know?
Well, that was probably GPR, ground penetrating radar. Lidar doesn't penetrate stuff much.
Oh yeah. Hey, real quick, one last question too. And I don't know if this is like a fake news, but did anybody see the information on where they they froze light?
Uh, you're talking about they've been doing these things where they, quote, slow the speed of light down to 10 miles an hour or something with materials essentially kind of very high index of refraction materials. I haven't seen any news recently about that, but is this
Oh,
something that you've just seen?
there are news. I think they managed to create something that like an Einstein Bose condensate with only photons. So it made huge news like last week, and the reported density, of course, of that thing is very big, and so you wouldn't expect this result from just photons of light. But yeah, that at least that's what on the popular media. I haven't looked at the original paper.
Well, I'll look this up. I'm not, because I don't listen to the news anymore. Stuff like this gets right by me.
All right. So I'm gonna try and have some pop up science chat rooms in this house as well throughout the week, but I don't always get around to it. So keep your eyes open for both Ben's house and Scientific Discourse for pop up rooms, and then for Shamash and John's on Wednesday and Friday, respectively. Thank you all very much for another chemistry room, spending time with us. I'm going to leave you. Hey, I'm not going to play blues. I'm going to play a rock and roll song by Joe Cocker. And the room will end after the song is done. It's about